In this lecture, we continue our discussion with Avrami kinetics. In the last lecture, we had arrived at these two expressions where the amount of beta that is formed in a system of volume V is given by this expression, where I is the nucleation rate, r tau is the radius of the nucleus that was formed at time tau, and integrating the whole thing. If we divide this particular expression by the system volume V, we get the fraction beta transformed as this, with basically the volume term cancelling out. In the last lecture, I had also mentioned that this is true for small values of transformation or small fraction of beta transformed. Now, why is that? Well, this model that has been presented so far allows nucleation to take place randomly anywhere in the material. Hence, and it allows the nucleus that is formed to grow indefinitely. What that means is, let us say we have some nuclei that are formed and then they are allowed to grow. As long as they do not impinge on each other, this expression or the fraction transformed given by this relationship will remain valid. However, one can visualize a situation where two nuclei could well impinge onto each other, but the mathematical model does not allow for this impingement. You can have a situation where a beta phase is already existing and a new nucleus, since nuclei can form randomly anywhere, a new nuclei could form and start to grow within the region which is already transformed. In fact, it can be best be illustrated by the simple simulation of beta particles nucleating and growing. So far as the amount of fraction transformed is small, they do not impinge on each other, whatever we have derived is correct. But if we allow further growth to take place, then you can clearly see, as further impingement goes, as further growth goes, so as growth continues to take place, you can see that the particles are growing into each other, and as transformation is allowed to continue further, we will also see nuclei forming inside the already transformed material, which of course is not physically possible, but this model has this particular flaw which needs to be sorted out. And I can also see that the volume transformed can keep growing indefinitely. So, how to take care of this, and let us look at that. How do we take care of that? So, as we have seen in that simple simulation, that the volume of beta transformed increases without bounds. So, this volume transformed V beta is represented as V beta superscript E, where E stands for extended volume. And this extended volume, as time progresses, increases without any bounds. and we would also have already seen that part of this extended volume lies within the previously untransformed alpha, and part of it lies within the already transformed alpha. So, the volume which lies within the previously untransformed alpha is the real volume, while the volume which lies within the transformed alpha is imaginary. And we have to take into account both the real and the imaginary volumes. So, we need to determine what is the true or real volume of transformed beta. How do we do this? Let us say at time t, V beta is the true volume and V beta E is the extended volume. At time t plus dt, true volume increases by dV beta and extended volume increases by dV beta E. And again, this increment in the extended volume, part of it is real and another part of it is imaginary, which has extended into the previously transformed alpha, while the real one is the increment in the previously untransformed alpha. Now, we had made an assumption that we had random nucleation inside the entire volume of the system. What that means is that at any given time V minus V beta upon V, where V is the volume of the system, V beta is the true volume. So, therefore, true volume of the transformed beta. So, V minus V beta upon V would be the fraction of untransformed alpha at any instant time t. At t, at any instant, this represents the fraction untransformed. Hence, if the nucleation is random, then probability of a nucleus forming inside the untransformed alpha will be V minus V beta upon V. That is the fraction of untransformed alpha. So, this represents probability of volume increment of beta inside untransformed alpha. Alternatively, it can also be looked at that the part of dv beta E as we in increment of time dt, the increment in the extended volume, the fraction of it which lies inside the untransformed alpha is given by this probability, and hence the increment in true volume of beta as we go from time t to t plus dt is then given by dv beta E times this probability v minus v beta upon v. So, this then is the key relationship between the increment in true volume to the increment in the extended volume. If we divide both sides by the volume of the system V, then I can write this as f beta on the left hand side, dv beta upon v is equal to df beta, the change in the beta fraction. This is equal to, if I look at this square brackets first, well, this can be written as 1 minus f beta times the increment in extended volume upon the volume of the system. Now, this is a straightforward equation. From here we can now get a relationship between V beta and V beta extended. So, if I look at this expression, I can write this as d f beta upon 1 minus f beta equals dv beta E upon V. If I integrate both sides, I will get minus ln 1 minus f beta equals V beta extended divided by the total volume of the system. This takes me to 1 minus f beta equals exponential minus V beta E upon the total volume, and the final expression we would get for the true fraction of beta transformed from here, just rearranging the terms, equals 1 minus exponential minus V beta E upon V. So, this gives me a general form of the true fraction transformed in the transformation from alpha to beta being given by 1 minus exponential minus the extended volume upon V. And how do we know what the extended volume is? The extended volume is given by this relationship. Which means now we need to plug in the nucleation rate here, how the nucleation rate is changing, if it is changing or it is constant, how the size of the beta particles are changing, what kind of growth kinetics they are following. If we plug this in, substitute in this, we would get the kinetics of phase transformation. So, let us start with a few simple cases. In fact, just start with the simplest case where we assume that the nucleation rate and the growth rate are constant and the nucleation takes place throughout the transformation at a constant rate. So, the nucleation rate I is constant throughout the transformation and the growth rate V is also a constant throughout the phase transformation. What this means is that at any time t, so at time t, the nucleus which formed at time tau, its size is simply, as we had already noted in the last lecture, is simply V times t minus tau. And we rewrite the expression for extended volume as 4 pi by 3 V. Since the nucleation rate is constant, I comes out of the integral and within the integral replace r tau by V times t minus tau, and in fact since V is also a constant, it will come out of the integral and become V cube, and inside the integral you would have t minus tau cube d tau. And if I integrate this, this would be 4 pi by 3 times the volume of the system times the nucleation rate times the growth rate V cube, and the integral after integration would be t minus tau to power 4 divided by 4 with the limits 0 to t. So, my extended volume then becomes, I put in the limits, at t this will be 0, at 0 if I put in it will be t to power 4, and hence we would get pi by 3 V I V cube times t to power 4. So, this is the extended volume at any time t for the situation where nucleation rate is a constant and the growth rate is a constant. And remember, growth rate is a constant for situations like interface controlled growth, for example, and an example of an interface growth control system could be alpha iron at high temperature when cooled down transforms to gamma iron. So, alpha iron, which is a body centered cubic phase, changes to FCC, where the growth kinetics would simply be controlled by atoms jumping from the parent phase, the alpha phase, to the nucleus, which is the gamma phase or the phase centered cubic phase. So, now this extended volume, now I can substitute in this expression to give me the rate or the fraction transformed at any time t to be written as 1 minus exponential, and I substitute the extended volume. So, the thing that will cancel out is basically the system volume. So, we do not want to be dependent on the system volume, and this would simply be minus pi by 3 V I, not no V will not be there, V is cancelled out, I times the growth velocity small v cube times T2 power 4. If I lump all of these together, since all of these are constants, the nucleation rate as well as the growth rate, I can lump it into some constant parameter k. Then f beta would simply be 1 minus exponential minus k T2 power 4. So, this is telling me how the fraction of beta is transforming as a function of time, and important thing to note here is that the time has an exponent of 4. This is characteristic of a transformation in which the nucleation rate is a constant and a growth rate is a constant. What would happen in a case where, let us say, the growth rate was parabolic and we keep the nucleation rate constant? So, we have a second case. If I call this as, let us say, case 1, then let me call this as case 2, constant nucleation rate parabolic growth rate. It would be interesting to analyze this. So, what we have is that r tau, the size of the nucleus that was formed at time tau, would be given by a constant b times t minus tau to power half. And what that means is that in this case I have to substitute for r tau in the integral, and the extended volume v beta e then is simply v times 4 pi by 3 I b cube integral 0 to t minus tau to power half d tau. This will not be half, it will be cubed, so this will become 3 by 2. If we integrate this, we would get v times 4 pi by 3 I b cube t minus tau to power 5 by 2 upon 5 by 2 with the integration limits 0 to t, and there is a minus, note the minus sign as well. After putting in the integration limits, we would get v 4 pi by 3 I b cube times, well actually this 5 by 2, this would become 8, this would become 15. So, 8 pi by 15 I b cube t to power 5 by 2, and hence the kinetics of transformation, fraction of beta transformed as a function of time, which is given by 1 minus exponential times the extended volume upon v, exponential of that is 1 minus exponential minus 8 pi by 15 I b cube times t to power 5 by 2. This, the terms in this are all constant, b is a constant, I is a constant, and if I call this as that parameter k, then the fraction beta transformed for this particular situation of parabolic growth, f beta is given by 1 minus exponential minus k t to power 5 by 2. So, here you note the exponent here. In the previous case of constant nucleation rate and constant growth, we had an exponent of 4. In the situation where we had a constant nucleation rate but a parabolic growth, the exponent is not 4 but it is 5 by 2. Similarly, we can consider other cases. I will consider a couple of other cases in the next lecture, where how the exponent changes when I change my nucleation rate or the growth rate kinetics, how the overall kinetics changes or the exponent in the Avrami relationship changes would be explored, and I will stop here.